So it's really hard to guess which questions we're going to answer and which ones will be sort of forever imponderable, or maybe just imponderable for like a million years. But it helps anyway to know where we stand now. So I'd like to give you a little quick overview of what we know about physics. It's going to be very non-technical, so it will be non-quantitative. So it means I can't like really tell you where we are, but just sort of outline it. So these are our best theories of fundamental physics today. Strangely, we don't really have one, we've got two. One is called the Standard Model, and it covers all three forces except gravity. There's the electromagnetic force. So everything about electricity and magnetism and light is the electromagnetic force. The forces that you notice when you study nuclei of atoms are the weak nuclear force and the strong nuclear force. There are two. And these are all covered by the Standard Model. And these are described using quantum mechanics, which I won't say much about, but it's really important because general relativity is our theory of the other force, gravity, and that is not described currently using quantum mechanics. That does not fit in. So there's the split in our understanding of the world where these first three forces we understand in one theory and the other in the other theory, and we can't really fit them together. Although in that first slide where I showed you that very impressive formula, they were sort of slapped together in a way which is sort of good enough for government work. Now the Standard Model describes both matter and forces using quantum mechanics. So there are particles that constitute matter, like electrons, which are these little guys labeled E minus because it's negatively charged. And there are particles that describe forces, like the electromagnetic force. The electromagnetic force is carried by particles called photons, which are drawn in this cute wiggly way here. Gamma is a name for a photon. And what the Standard Model gives you is a bunch of formulas for calculating the probabilities that various events will occur when you smack particles into each other. So this little picture is a kind of symbolic diagram of two electrons coming in. They're both negatively charged and they repel each other. And the way they do it is they exchange a photon and then they push away from each other and go out. But because it's described using quantum mechanics, we don't know for sure how they will shoot out. We just know the probability that they will shoot out with various different possible velocities. And the Standard Model gives you formulas that lets you calculate those probabilities, both for this particular force that involves the photon and the other forces that show up in the Standard Model, and for other particles besides electrons. But interestingly, both matter and forces are described by different kinds of particles. So here are all the particles in the Standard Model. So there are particles that carry forces. So there's the electromagnetic force, the weak force, and the strong force, and each of them has one or more particles that carry it, some with very cute names. And then there are particles that constitute matter. Matter, strangely, comes in three generations. The first generation includes all the matter that you see around us here for the most part. Namely, there are electrons. So our atoms are full of electrons. Now, our atoms also have protons and neutrons in them too. Those are the main other things to think about when you think about atoms. But those protons and neutrons have smaller constituents that have been discovered called quarks, and they're just called the down and the up quark. And then there's a ghostly counterpart of the electron called the electron neutrino. That's this U sub E guy. And that's a neutral particle, as the name indicates. And neutrinos, I call them ghostly because they're extremely hard to detect. They only interact with things via the weak force, which is weak. So they're very hard to catch. Now, the strange thing is that in addition to those, there are sort of copies of them called the second generation, consisting of some other particles that are heavier, and then some in the third generation, which are still heavier. But these other guys tend to decay very rapidly into particles of the first generation. So they don't hang around. So they're particles that you pretty much only see when you have very energetic cosmic rays shooting down from the heavens, from various energetic events occurring stars and so on, or you make them yourselves using particle accelerators. And that's what people do with particle accelerators is create and study these more exotic particles. And then finally, there's one more that you've probably heard of called the Higgs boson, which interacts with all the particles that have mass, and its interaction with those particles is what gives them mass. And so you could draw a little chart of all these particles and how they interact with each other, or which ones interact with each other, I should just say. So the blue curves here are just ways of indicating that one particle does interact, that does do something, and it bounces into another particle. So for example, the Higgs boson interacts with lots of different particles because lots of particles have mass. It does not interact with the photon because the photon has zero mass. Light is light. It doesn't have any mass. The Higgs boson interacts with itself because it has mass, and so on. So like the photon does interact with the electron, as I showed you in that earlier slide, and it interacts with the electron's partner particles of the second and third generation, but it does not interact with the neutrinos, of which there are also three, because those are electrically neutral, and so on. So it's a rather complicated pattern. It's not anything that anyone would have decided, like, okay, let's make up a theory of physics. Hey, I'm going to try this. That's not how it goes. It's just you do experiments and you discover that there's all this stuff going on and you have to account for it. So it's to make quantitative predictions, of course, you need numbers. And so, in fact, there are 25 numbers in the standard model of physics, which describe the precise strength of the various interactions that are involved. And surprisingly, 22 of them, a lot of them, involve the Higgs boson. That is because the Higgs boson is interacting with lots of things, giving them their mass, and also doing some other things, like perhaps, and I'm assuming it's true here, making the neutrinos do extra stuff called oscillate. So there are these 25 numbers that we don't know how to calculate from first principles. The only way we can figure out these numbers is by actually doing experiments in the lab. And that's part of the standard model, just this list of numbers. So having heard this, you should, unless you're extremely jaded, you should be bursting with questions like, what's going on with all this stuff? So here are a few of the obvious questions that might immediately leap to mind, like, why are there 3 forces in the standard model? Why not just 1? Wouldn't that be simpler? Or maybe like 17, if you really want to make it exciting. Why are there 3? Why does each generation of particles have 2 leptons and 2 quarks in it? There's some kind of weird pattern there, but we don't know really why. Why are there 3 generations of particles? We're pretty sure that that's true because we can do experiments smacking some particles into others where like particles of every generation are getting created. So unless the remaining generations of particles are extraordinarily heavy, we know for sure that there are just 3 but we don't know why. And then, of course, why did the 25 numbers that I alluded to have the values that they do? So now there are some theories, so-called grand unified theories. People making these theories are not extremely modest, who offer plausible answers to the first 2 questions. There's, for example, a theory called the SO10 grand unified theory, which shows you that, like, yes, everything is beautiful in this theory, but only if you have 3 forces and only if each generation has 2 leptons and 2 quarks and so on and so on. It's really great. It's really beautiful. We're not sure that that theory is true, but it's really interesting because of how it seems to make sense out of this mess of information. The third question, why there are 3 generations of matter particles, we're really much more clueless about that. And the fourth one, why do these numbers take the values they do? We're completely clueless about that. People do try to make up formulas for these numbers, but none of them seem very convincing. We just don't know a mechanism whereby these numbers would arise. Well, there are, people have theories of mechanisms whereby they arise, but none of them are extraordinarily convincing. So it's difficult.